We're going to begin Chapter 6, which is titled Thermochemistry. Every chemical reaction obeys two fundamental laws, the law of conservation of mass and the law of conservation of energy. We discussed the law of conservation of mass and mass relationships between reactants and products back in Chapter 3. Here we're going to look at the energy changes that accompany chemical reactions. All right, let's get started. First, let's define what energy is. Energy is the capacity to do work. This term energy is used a lot, but it's really an abstract concept. Energy is known and recognized by its effects, but you can't see it, you can't touch it, you can't smell it, and you can't weigh it. Back in Chapter 5, we defined work as force times distance. But you see here that there are other kinds of work. All forms of energy are capable of doing work. Here I'm showing you several different types. There's radiant energy, thermal, chemical, nuclear, potential. There's even kinetic energy. You are responsible for recognizing the different types of energy. The most important thing for you to remember is that there is a law of conservation of energy, meaning that the total quantity of energy in the universe is assumed to be constant. So you can't create nor destroy energy, just like you can't create nor destroy mass. So since you can't create it nor destroy it, basically what happens is that they interconvert between one another. So when one form of energy disappears, some other form of energy of equal magnitude must appear, and vice versa. That principle summarizes what the law of conservation of energy is. Almost all chemical reactions either absorb or produce energy, and generally this energy comes in the form of heat. It is really important for you guys to understand the distinction between thermal energy and heat. Heat is the transfer of thermal energy between two bodies that are at different temperatures. When we talk about heat, it usually refers to heat flow, right? So heat flow from a hot object to a cold object. But although the term heat by itself implies the transfer of energy, we usually talk of heat absorbed or heat released when we describe the energy changes that occur during a single process. The important thing here is that when we measure temperature, for example, when you use a thermometer, you're measuring the temperature of something, that does not equal the thermal energy. Temperature is a measure of thermal energy. I want to stress those three terms just one more time. So thermal energy is the energy that's associated with random motion of atoms and molecules. That was in the first slide. Heat is the transfer of thermal energy between two bodies that just happen to be at different temperatures. Okay, so temperature does not equal thermal energy. Temperature is just a way for us humans to be able to measure the thermal energy in a system. Remember, the thermal energy is just the random motion of atoms and molecules. So the only way that we could measure that is through temperature. Okay, but it does not equal thermal energy. It's just a measure of thermal energy. Don't get too caught up in these. We'll go over them over again and again throughout the chapter. Now we're able to define thermochemistry. Thermochemistry is the branch of chemistry that studies the heat changes in chemical reactions. To analyze energy changes or heat changes within chemical reactions, we must first define what a system is. Okay, so the system is the specific part of the universe that is of interest in the study. So the beaker where the reaction is happening, or the vessel where there's stuff going on. So just basically the part of the universe that is of interest to you for that particular problem. The surroundings is everything else. So basically the rest of the universe outside of the system. Here I'm showing you an example of what a system could be. A system here is represented by water in a flask. And there's three types of systems. There's an open system, a closed system, and an isolated system. An open system is one that allows the exchange of both energy and mass. So let's say, for example, I was to heat this flask. Well, I'm going to get water vapor leaving the flask as I keep heating this flask, which turns into the mass changing. And of course, there's going to be heat transfer because I'm warming up the system. So that's an open system. When you can have the exchange of both energy and mass with the surroundings, that's open. If you have a closed system, so now I've put a top on this flask, so I can still heat it, right? The heat can still go in and out of this system, but no mass can leave because I've closed it off. So this is called a closed system. It only allows the exchange of energy, but not the exchange of mass. An isolated system means that it's isolated. Okay, nothing leaves, nothing goes in and nothing goes out. So I can't have any exchange of mass and I can't have any exchange of heat, of energy. So think of it like a thermos or a vacuum flask or something like that. So nothing can go in and out. These are the three types of systems that we're going to be working with in this chapter. The combustion of hydrogen gas and oxygen is one of the many chemical reactions that release considerable quantities of energy. In this particular case, we're going to label our system as the hydrogen, the oxygen, and the water that's being created. The surroundings is basically everything else, the rest of the universe. Because we can't create nor destroy energy, the energy that's lost by the system must be gained by the surroundings. What that means is that the heat generated by this combustion process is transferred from the system to its surroundings. This reaction is an example of an exothermic process. Exo comes from the Greek word meaning outside. And of course, endo comes from the Greek word meaning within, but let's stick with exothermic process first. An exothermic process is any process that gives off heat, basically transfers thermal energy from the system to the surroundings. An opposite process would be an endothermic process. This is a process in which heat has to be absorbed by the system from the surroundings. So you have to supply energy to the system for it to happen. When you heat HGO, which is a solid, it's going to decompose into mercury and oxygen gas. But you actually have to put heat to this solid to break it up. So that's what I mean by an endothermic process. This process, the system here is of course your HGO and the mercury that you're getting as a product and the oxygen gas. But for that solid to decompose, you have to put in heat, you have to put in energy. So that's an endothermic process. You will be responsible for knowing the difference between exo and endothermic processes. Let's talk about this a little bit more. Here I'm showing you a schematic of an exothermic and endothermic process using the two chemical reactions we just talked about. In exothermic reactions, the total energy of the product is less than the total energy of the reaction. That's why heat is given off by the system. And that's why the system ends up with less total energy once that reaction is over, because it's giving it off to the surroundings. When you have an endothermic process, like you have that solid, mercuric oxide, and you have to heat it, you are inputting energy into that system. So when that reaction ends, the system has more energy than what it started with. So again, an endothermic process is something that absorbs heat or absorbs energy from the surroundings. Make sure you understand these two processes, since this entire chapter will be based upon exo and endothermic reactions. This question reviews the concept of the three different types of systems. So I would like you guys to try and see if you can classify each of the following as an open system, a closed system, or an isolated system. First one is milk kept in a closed thermal flask. What do you think that is? Isolated, closed, or open? How about B, a student reading in her dorm room? And how about C, air inside a tennis ball? Remember the difference between the three different types of system. An open system, you can have a transfer of mass and energy. A closed system, you can have a transfer of energy in the form of heat, but no transfer of mass. And an isolated system is nothing goes out, nothing comes in. So no mass transfer and no energy transfer. See if you can answer those. Let's try this one. It says an endothermic reaction causes the surroundings to A, warm up, B, become acidic, C, condense, D, decrease in temperature, or E, release carbon dioxide. I'm going to help you with this one. Well, I know it's definitely not become acidic, condense, or release carbon dioxide, because that has nothing to do with endothermic or exothermic. Endo and exo have to do with the heat changes in a reaction, so definitely those are out. I'm left with A and D. Let's think about what an endothermic reaction does. An endothermic reaction uses energy from the surroundings, so the system needs energy from the surroundings to actually happen. So if the system is actually absorbing energy, then the surroundings must be giving that energy. So in other words, think of the example I gave with mercuric oxide. That was a solid. That was the system. The system is the mercuric oxide. You need to supply energy to that system. So therefore, if you're supplying energy to the system, then the surroundings must get cold. If you're making the system hotter, right? If you're putting heat into the system, then the surroundings must be releasing heat. So it must be getting colder. So it must be D. An endothermic reaction causes the surroundings to decrease in temperature because the system is sucking up heat or absorbing heat. So it's raising in temperature, therefore the surrounding must decrease in temperature. Remember, energy is neither created nor destroyed. So if one part takes up energy, then the other part must release that energy. This is all I want to talk about for now in this video. I'm going to resume with section 6.3, which is an introduction to thermodynamics. See you later.